In the previous installment, I introduced my project of designing a flatbed knitting machine system that can be 3D printed at home. But knitting machines have been around for a long time, dating all the way back to William Lee's invention of the stocking frame in the late 1500s. My project aims to address what I thought was a bit of an unfilled niche for crafty folks like myself, but I certainly didn't invent the underlying concept or mechanism, and I wasn't even the first person to attempt a DIY machine, as we'll get into shortly. So before we zoom in on the details of my design and process, I thought it would be useful to set the scene a little by reviewing some of the many examples of knitting technology and their impacts that came before it. Knitting machines come in a wide range of shapes, sizes, and applications, from plastic tabletop toys to computer-controlled industrial behemoths that are tuned to knit one particular item over and over. What even these diverse machines share is their basic mechanism. Unlike in hand knitting, where a row of active stitches is arranged on one pointed needle and worked off sequentially one at a time onto a second needle, in machine knitting, each column of stitches has its own hooked needle arranged in an array or a circle. A loop of yarn sits around the shaft of the needle, and the next row of stitches is formed by catching the incoming strand of yarn in each needle's hook, pulling it through the existing loop, and then pushing or dropping the old loop off of the needle so the new stitch can take its place before returning to its home position. A lot of machines use latch hook needles for this, but there are other needle designs that can accomplish the same thing. This stitch-forming action is typically controlled by passing the needles through a series of cams, an arrangement of levers and ramps that physically push the needles in and out along a predefined path that's coordinated with the yarn delivery. Incidentally, I think this is a pretty cool physical demonstration of the concept of pipelining, which is also a really important feature of modern computer processors that allows them to work so quickly. The execution of an instruction involves multiple stages of operation. Pipelining enables a processor to work simultaneously on different instructions by performing a different phase for each of the multiple instructions at the same time. The processor overlaps operations by moving data or instructions into a conceptual pipe, with all stages of the pipe processing simultaneously. Similarly, by breaking the process of forming a stitch into stages and having each stitch on its own independent needle, you don't have to fully complete each new stitch in the series before starting to process its neighbor. And this can reduce the overall processing time of the whole series. Although, in this case, the pipe isn't so much conceptual as it is an actual physical tunnel. Anyway, the big industrial machines are made to satisfy pretty different goals and priorities than most machines aimed at individual craft knitters, especially when it comes to things like size, speed, serviceability, and cost. Since the machine I'm building is for home, or at least small-scale individual use, we're mostly going to ignore those large-scale production machines for now and focus on what's reasonable to expect from domestic models. So, a domestic knitting machine typically comes in one of two different basic shapes. There's the flatbed style, where the needles are laid out side by side in a big long line, and the cam housing moves back and forth across them, usually pushed by hand. These are primarily used to knit flat panels of knitted fabric. Then there's the circular style, where the needles are arranged in, you guessed it, a circle, and the cam housing, or the needle cylinder, goes around and around and around, usually by cranking a handle, knitting in a continuous spiral that forms a seamless tubular fabric. But wait! Everything I just said is true, except for all the exceptions. Because apparently machine knitting is a bottomless rabbit hole of edge cases. Many models of flatbed machine can be fitted with a second bed of needles in the opposite orientation, called a ribber, which allows them to form stitches facing the other side of the fabric. This not only opens up an exciting world of textured stitch patterns, it also allows flatbed machines to knit tubes by knitting only the top bed's needles in one direction and the bottom bed's needles on the return pass. On the other hand, some circular machines can be persuaded to knit flat panels by carefully stopping at a specific point and knitting back in the opposite direction. Some circular machines can also be fitted with a ribber attachment, which, like the flatbed ribber, allows selected stitches to face the other side of the fabric. But unlike the flatbed ribber, only seems to allow tubular knitting when the ribber is attached. You can't change directions to knit flat panels at least not on the examples I've seen. Many popular flatbed machines of the mid to late 20th century could be programmed to knit patterns automatically, using buttons, punch cards, or computer software to select certain needles to knit or not at different times with different colors of yarn. This sort of pattern programming isn't a common feature of home circular machines, but I have seen one extremely cool example of an antique machine that uses a secondary jacquard drum to mechanically engage and disengage needles to do multicolor designs in a pattern set by the user. It's really cool. And for the most part, if your machine doesn't go out of its way to do these fancy tricks for you, you can still achieve these effects by manipulating the needles and yarn by hand. Sometimes this hand manipulation still ends up being faster than hand knitting, and sometimes it really, really doesn't. While the very first knitting machines followed the flat or frame design like William Lee's, and circular knitting machines weren't developed until a couple of centuries later, it seems like the circular machines were probably the first to be widely marketed as a sort of domestic appliance, as opposed to a tool for tradespeople. Though even these so-called family machines were often pitched with this sort of hustle culture, make money in your spare time undertone. Once someone did get the idea to produce them for homemakers, though, flat knitting became popular enough to warrant a kind of mid-century Cambrian explosion. So there's an impressive range of antique machines out there. Everything from children's toys to sophisticated electronic models, which you can get a taste for by checking out channels like The Answer Lady Knits, for example. But I've only heard of a couple of models that are still being produced today. This means that if you want to pick up a flatbed knitting machine other than, say, an LK150, you're kind of at the mercy of the buy and sell classifieds or auction sites. And it's worth noting that these secondhand machines, especially if they've been kept in good condition, are often a little bit of an investment. Several hundred or even thousands of dollars for the machine, plus potentially hefty shipping fees if you're not lucky enough to find one for sale locally. If you're more interested in buying a machine than building one, Carson at Knit Factory Impel did a pretty great roundup of commercial machines that are currently on the market, as well as what to look for in a secondhand machine. Circular knitting does seem to be having a bit of an it girl moment, so it's possible to find several styles at various price points that can be purchased new from the manufacturer today, as well as refurbished antique machines, also very expensive, and they've also had a bit of a boom in DIY designs as well, as we'll look at shortly. So each of these designs has their strengths and weaknesses for different applications, but in general, I'd say flatbed machines, especially ones with the ribber option, are more versatile, especially because you can easily modify the width of the work by increasing or decreasing the number of needles in use, which just isn't as straightforward for a circular design. The sheer variety and inventiveness of these machines is kind of magical to behold, but it did make researching and writing about this part of the background a little bit overwhelming, especially because cataloging all this history and diversity from scattered sources wasn't really the point of the project, even if it feels super relevant and important. Like I said, just edge cases. Like every time I thought I could draw a nice clear line around some category or statement, I'd stumble across some bizarro counterexample, like a flatbed machine that folds up for travel. In fact, one of the very few published books about modern domestic machine knitting that I was able to get my hands on stated quite definitively that no plastic double bed machines existed. And then like 2 weeks later, the YouTube algorithm is like, hey, psst, buddy, psst, check out this video about the Bond Elite Ribber. And I don't mention that to imply any shade towards the author because the book otherwise seems great, just to highlight that describing the scope of these machines isn't exactly a straightforward question even for the recognized experts. And I haven't even really touched on the variation in features and accessories like lace or garter carriages, automatic color changers, or yarn tension management. Knitters, sewists, textile artists in general, crafty maker types, have a rich history of staring off into the distance beyond what we can get off the shelf and thinking, I bet I could make that. And it turns out that applies to our tools too. Some folks have hacked the guts of machines that are already out there, reverse engineering the interfaces of old electronic knitting machines so that they can communicate with modern computers. Some notable projects in this lineage include Steve Conklin's original work on the emulator, Becky Stern and Lady Ada's tutorial on hacking the Brother KH930E, which many subsequent projects reference, Amy Wubowo and team's Nintendo-inspired Airbnb hackathon project, which I had the pleasure to see Amy speak about in person, and Sarah Spencer's Knitting Network Printer, which can, quote, accept an image from the computer over the network with more than 2 colors in any single row and can knit it hands-free. The AYAB, or All Yarns Are Beautiful, open source project also uses existing knitting machines, but takes a slightly different approach to the problem. Instead of using the original interface, it's replaced the custom Arduino shield, which provides an alternative means to control the knitting machine's guts via the computer. Knittic was another open hardware project by new media artists Varvara Guyayeva and Mark Kennett, who explicitly place knitting machines in a legacy with other personal digital fabrication tools such as 3D printers and CNC machines. The research on reverse engineering of knitting machines made us realize that the electronic knitting machine was the first digital manufacturing tool at home that has been totally overlooked in the age of digital fabrication. Recently, a team at Carnegie Mellon published a paper about augmenting purely mechanical machines with electronics, not to control the machine itself, but to guide the user through an otherwise kind of opaque and intimidating process, especially for beginners, by providing sensor information about the state of the machine and the knitting. And if you'll allow me to get up on my soapbox for a second, this approach is particularly interesting to me because, unlike so much of what tends to get labeled technological progress, the purpose of these enhancements isn't to try to abstract away the complexity of the process, but to demystify it. The eventual goal isn't to displace skill work from humans onto machines or to divorce the design process from the manufacturing, but to support interactive skill development, intuitive experimentation, and human effectiveness. In addition to commercially produced machines and projects based on them, I've found several cool examples of DIY knitting machine projects, which are new builds, not based on hacking or retrofitting pre-existing commercial hardware. 2 popular 3D printable circular sock machine projects are available via Thingiverse. One fairly basic machine, originally uploaded by a user called Diffle, and significantly remixed by another user known as Jeeping Johnny. And there's another pretty sophisticated machine with a ribber attachment, which was submitted by Steve Turner, aka Mr. Roboto 19, which is based on the Laguerre style of antique circular sock machines. There are also a few other makers who have shared demonstrations of experimental works in progress for hand-operated circular machines as well. I have printed and built my own version of the Diffle Jeeping Johnny CSM, and in fact, it was one of my household's main motivations to finally invest in a 3D printer, which in turn enabled this project. So, pretty cool. In my experience, these small hand-cranked styles of circular machines, they can be pretty speedy and sort of equal parts fun and frustrating to operate when creating simple tubular fabrics, but they're not as versatile as flatbed machines when it comes to knitting larger or more complex shapes. I've also found that due to the circular layout and the small number of needles, they can be a little bit tedious to use for intricate or flat panel designs. On a somewhat larger scale, we find projects such as Circular Knittic and OpenKnit. Both are open source, open hardware projects featuring Arduino microcontrollers and robotics for mostly hands-free operation. Circular Knittic, as the name suggests, is a circular machine which knits tubular fabrics, and it's positioned more as a kinetic art installation rather than a utilitarian tool. While OpenKnit is a double bed design capable of manufacturing a wider variety of shapes. Both machines occupy a pretty significant physical footprint, which may be impractical for a hobbyist space such as mine, and building OpenKnit requires a few specialist materials and tools or techniques. At the time of writing, it's tough to tell if either project is actively maintained. And this leads us to Knitterate. Unlike the other projects in this section, Knitterate is not open source, or at least not anymore, but it does appear to have grown out of the OpenKnit project, and it targets a similar makerspace digital fabrication niche, claiming to offer, quote, the best of both worlds, a compact version which a hobbyist can have at home or share with others at a local makerspace, and also the capabilities of an industrial knitting machine. On the other hand, The listed price of nearly £16,000 could prove just a tiny bit prohibitive for hobbyists whose main goal is not monetization. And while the machine can knit a very large variety of shapes and patterns, the way they've prioritized autonomous operation does apparently rule out some common knit features that I personally would want to have access to, like intarsia and especially short row sock and stocking heels. Now, I want to stress that this is by no means a comprehensive history of knitting machines or an exhaustive list of related projects. As I mentioned earlier, there's just like a ton of industrial machines out there, and they do tend to prioritize different operational goals than I do as an individual artisan. And I found that researching industrial machines just wasn't turning out to be super relevant or helpful beyond the absolute basics. So I really didn't do a deep dive into that literature. Unfortunately, while there seems to be a decent amount of such literature available about the industrial use case, I really kind of struggled to find similarly authoritative sources for the sort of domestic or artisan machine knitting I was interested in, especially academic writing that wasn't prohibitively paywalled. And I'm not the only one who's noticed this gap in the scholarship. Richard Candy wrote that codifications of knitting technology describe factory machines in great detail, but say little of domestic ones. Although I can't tell whether he elaborated on that point because that's about where the article's free preview ended. Lynn Abrams and Lynn Gardner also describe how this niche slips into what they call an analytic gap that artificially divides the history of knitting into opposing paradigms. The study of knitting as a craft practice treats it as a traditional activity, albeit adapted to modern sensibilities and taste, and focuses overwhelmingly on the techniques and designs of the hand knitter. Handcraft, in this narrative, excludes the use of hand-operated machines, an omission that downgrades the skill required to produce garments this way and perpetuates a false distinction between hand and machine-made knitwear. The industrial paradigm, on the other hand, is dominated by studies of factory production that subordinate the economics of hand knitting and regard it as an outmoded and unprofitable practice superseded by mechanization. Given this gap, I ended up citing a few atypical sources. User-generated content like blogs, vlogs, wikis, and tutorials may not typically be viewed as a resource for academic writing, and I completely understand why. I mean, any fucking clown can start a YouTube channel, am I right? But I also think it's a mistake to entirely dismiss the value and power of community knowledge like this, especially when it comes to topics that have been a bit neglected by traditional academia. Luckily, there is a thriving and generous culture of knowledge sharing here on YouTube, and so much of what I've learned about how these machines work, where they come from, and what it's possible to achieve with them is thanks to binging hours of content by creators who so enthusiastically share their knowledge and experience. There's way more great channels out there than I could possibly name, but you'll find many of my favorites in the citations. Now, I did try to do a thorough review of the existing literature, but I have no doubt that there are corners of this topic I haven't seen yet. So if you know of resources or exciting projects that I haven't mentioned that you think I should check out, I would love to hear about them. So please let me know down in the comments. Okay, so this might all sound like a lot of knitting machine options, and you might be wondering why I thought it was worth adding another. When I looked around at what was out there, I realized that nothing already on offer was quite what I wanted. Many were very expensive, some were too bulky, too hard to find, too constrained in what they could do. I really wanted a flatbed style machine, one that's versatile, customizable, expandable, low cost, simple to build without specialized tools, and that would offer a good platform for future experimentation. Is that all? And all my cards on the table here, I'm also just a huge nerd who got really obsessed with solving the puzzle and seeing if I could build something that actually works. I thought a lot about what it would mean to shoot for hands-free operation like some of the other projects I'd seen, and I realized that it would probably mean sacrificing a lot of those other priorities I just mentioned. Not to mention adding just a ton of complexities to the project that I probably didn't have time for. I've done some electronics projects in the past, but I had no prior experience with robotics or motors. So I'd be committing to researching and learning yet another new skill set on top of my relative inexpertise in other mission-critical areas like 3D printing. Not only that, I started to realize that while there are definitely some computer-aided features that I think could be super valuable, a hands-free, set-it-and-forget-it knitting machine was something I didn't really want. I love creating things with my hands, and I was looking for tools to help me do it better, but I've become a bit more introspective about what I even mean by better. I keep wanting to say efficient, but if I'm saving time or effort, who or what am I saving it for? And to what end? That's not to say that automating some or most operations was a bad or wrong choice for the projects that chose it, because I think that better means different things at different times for different people in different contexts. Hell, I started learning to code in the first place so I could avoid doing certain parts of creative tasks that I personally found tedious. And I've absolutely leveraged the power of technology for the sake of precision or quality or repeatability or accessibility that would be hard for me to achieve without it. But to put it bluntly, after a lifetime of trying to take my one-of-a-kind or bespoke creative work to market, I am tired of internalizing the idea that the most important measure of any given activity's success or worth is whether it's optimized for capitalism. I don't want to scale right now. I want to be gloriously, interestingly inefficient, damn it. Anyway, the corporate AI hype machine was starting to pick up steam in parallel with this research, and I began to think a lot more about the difference between tools that are chosen to enable and those that are imposed in order to maximize profit. It almost started to feel like an act of resistance to focus on building something that's not actively aimed at distancing the craft from the craftsperson. This motif pops up again and again throughout knitting machine history. William Lee was refused a patent for his invention because Queen Elizabeth was wary of the disruptive impact it would have on England's pre-existing artisan knitting industry. The Luddites weren't anti-technology per se. Many were already using hand-operated stocking frames when some chucklefuck industrialist came along and tried to implement automated factory machines that made worse products but faster and cheaper, with less dignified, less safe working conditions for the remaining de-skilled factory workers. On the other hand, I am not trying to say that getting more done faster is a bad thing in and of itself. Sometimes speedy productivity is genuinely crucial for meeting a pressing need. For example, during World War I, home knitters were tasked with turning 10 pounds each of rationed wool into up to 30 pairs of warm and potentially life-saving wool socks for soldiers in the trenches. A skilled and industrious hand knitter could realistically get through about a tenth of that in the 3 weeks before the Red Cross reallocated the yarn to someone else. While knitters who were provided with a metal Gearhart machine could pretty comfortably get through their quota, at least once they got the hang of the machine. Jumping ahead to this century, Socks by Bob in Saskatoon has been able to provide thousands of socks and other warm winter accessories to unhoused community members across Canada, using hand-built motorized machines which can knit at a pretty blazing 90 stitches per second. Setting aside for a second the morality of the systemic context that led to people having these urgent and life-threatening needs, I think we can agree that valuing speed and scale is useful when the goal is helping as many people as possible not die of preventable causes. But the machines used in those two examples also showcase the point I made earlier about the sacrifices and trade-offs of this type of automation. The Gearhart machines used by the war effort knitters were faster than hand knitting, but they were still hand-cranked. So we're talking like a 10x versus Bob's 30x increase in output in the short term. Having personally knit 7 pairs of socks in 1 week on a hand crank machine once, I can pretty confidently say that I for sure would not want to do that every week indefinitely. So the robot takes that point for like sheer relentlessness, but the motorized machine achieves some of that speed and autonomy at the expense of versatility. all it has to do, all it can do, is go around and around and around. It can knit a very long tube pretty fast, but that tube has to be cut and finished into a sock by hand. The resulting sock doesn't have a shaped heel, which is a feature that even an expensive and sophisticated hands-free machine like the Knitterate doesn't accommodate. Now, I think this is largely because this sort of three-dimensional shaping requires a very different approach to weight and tension management that's honestly a bit tricky to convey to a human more precisely than like vibes, let alone trying to distill it into an abstraction suitable for a machine. The engineering required to make the leap from fast tube to fully automated full-fashion knitwear is non-trivial, but the hand-cranked machine is agile. She's a generalist. She can pivot. You want a tube? No problem. You want a different size tube? Let me switch cylinders. You want a short row heel? Fetch me my forks. You want a custom-fit gusset with a reinforced flap? I might spend a day swearing and weeping, but this baby and I can do it, which is still a damn sight better than the, infinity time it took me to never finish the last sock I cast on double-pointed needles. The point I'm kind of circling around is that the way technologies develop is the result of choices, not inevitabilities. Sometimes it feels like we're leaving something on the table if we don't add all of the popular bells and whistles, but adding more computer or more Taylorism to something doesn't inherently make it better or more sophisticated, and in some cases it can actively work against your design goals. You don't have to add, and that's okay. So, equipped with a big picture of what knitting machines can do and be and represent, I set to work on a system that I hoped might at least start to satisfy my own personal wish list. Coming up in the series, I'll show you how I got there, plus a closer look at the machine that tempted me down this rabbit hole in the first place. Until then, stay curious.